working with hydrogen. So he is set up where we are working together at sort of sponsored a project to look at how iron ore can behave under the kind of reducing condition kind of using hydrogen. So I think this morning and afternoon I will be going, as I said, you know about steel industry, you know about power industry. So most of this session today will be focusing on deep end of hydrogen. And hydrogen, as I said, we are working for a while, and I can tell you with authority that we are one of the best. So you can ask any question about hydrogen. So today we will go into deeper aspect of that. So PEM-based technology, that's we mentioned the electrolysis, but we'll be sort of coming from two other things. So while just remind ourselves the net greenhouse gas emission, that is gigaton equivalent. So that's 60 gigaton per year. If it is sort of, you are talking about 2020 around this time. And so if you want to have various scenarios, so if you implement policies and nationally determined contributions, because every country has we have to produce this much, then you need to follow this kind of path, net zero. So net zero, some countries will be 70, 80, some countries will be 50, etc. But globally, say, if you have to follow that kind of protocol and you limit below 2 degree temperature, or below 1.5 degrees. So these are, but what the point is that substantial reduction is required, and that's why huge renewable capacity already there. It is anticipated by 2026 4.5 terawatt of renewables in global capacity will be. And so even hopefully, I don't know what happens, so that if you electrify everything, that's the hydrogen. And decarbonization story, we know that not many options. So one option is CCS and one option is probably renewables and hydrogen. So if you look at the CCS,
can you back this time? So you are saying that for limiting 1.5 degrees centigrade, we have to make the greenhouse emission zero in 2100.
Something like that. That's the
Is it possible?
ambitious. Well, that's the thing. Cost and climate change. Which one want? Which one both? Or maybe at least even if you can limit somewhere or other, whatever trajectory you take, hopefully that will have a good thing. But if you this kind of do nothing, that will go like that. This is not the option. At least global consensus is not the option. So now carbon capture. Some people started what was happening in carbon capture and storage capacity. So million ton per year. So you can see that one yearly. So that was early development, advanced development, in construction, operational, and total capture capacity is right hand. So this is kind of million ton per year. So in 2020, so that's obviously that's going up. I think there are a lot of interest with carbon capture projects, and you can see that. But if you look at the operational, not much really still. So that's and that which country you think mostly US, but that's mostly US is operational kind of category, I guess. There are also Canada, Europe, China, few projects. So I know there are other projects also coming online. I know in Australia at least 3-4 projects that are being planned by the oil and gas companies like that. So things happening, but I believe we have to wait and see. So now let's move into the hydrogen story. So that's we discussed quite a bit, but let's go into the deeper end of that. So primary resources, renewable energy. Hydrogen is not an energy itself; it's an energy carrier. So we convert energy. You have got fossil energy, you've got other surplus energy, and then what we say electrolysis or other conversion process. You can liquefy it. You can load on a ship like LNG. So LNG you can set for liquid hydrogen gas maybe, something like that. And then liquid you can transport in other means, and we will look at that, some scenarios, what situation and what option of transport should be for hydrogen. Loading, unloading and also regasification, and you can put in a tanker, pipeline, and hydrogen station, refueling station, etc. So that's the way sort of if you look at the broad structure. So now you talk about the even smaller scale, so that you can have electric grid, you have supply, you have got solar can feed in, or wind, even other renewables, not only solar and wind. and then you can put in an electrolyzer, and electrolyzer produce hydrogen in compressing. You can transport it in a tube trailer, or then you can store it. You can put it in a refilling station, and as I said that 8 kilogram hydrogen per 100 kilogram for a bus, for example, this kind of configuration. You can have. This is another interesting system that some of the places that we say, oh, it's costly, it's expensive. But what about if we integrate with other industries? I don't know here how develop the sewerage system, so that wastewater treatment system, and wastewater treatment not only for cities but also for industries. You might need to. So wastewater uses a lot of oxygen. So you can have oxygen generated, as I say, 5 times hydrogen. You can have your wastewater treatment plant, and then you can have kind of treated. So you make 2-3 industries, this becomes a bit clumsy, but as long as you can supply the gas in the system, then overall you're making more efficient, more beneficial utilization of the energy. So that can be another configuration. But at the end of the day, you know what's the cost, because it has the capex, opex, and net CO2 emission reduction.
What is FCEV?
Which one? Fuel cell electric vehicle. This one? Fuel cell electric bus. So, fuel cell electric bus. That's right. So basically, on the top, usually there is a, I don't know, maybe 60 kilogram, something kilogram cylinder of hydrogen at 300 bar pressure, and here there is a fuel cell. So that supply the fuel cell power, and then bus.
Bus 8.8 kg hydrogen for 100 kilometers.
Something like that. But I think that has been more efficient. You get less hydrogen, 7 kilogram per plane, something like that. So this is a kind of one of my paper, one of my student Dr. Arash Arakani did that one. So that's so high demand and long distance, and it is the longest distance, highest demand. So this is kind of, we did some analysis, but that's kind of behind the analysis. There are a lot of numbers, but broadly the scheme of the results. So if you see high demand and short distance, you should think about liquid tank, pipeline, tank, tube trailer. If you have, on the other hand, say that you have a long distance but high demand, then pipeline, shipping, intercontinental transport, that sort of configuration you can have. So this is more on the transport evaluation of the hydrogen. So that, as we said, that you get electrolysis. That's what we're talking about. You can gasify also fossil energy like coal and coal particularly. And then steam. This is a common current. You can say 70, 80, even 90% probably hydrogen is made by that. Because coal hydrogen is only Chinese, as far as I know, and not other. Most of the places steam becomes reforming. For example, fertilizer plant, urea plant, wherever hydrogen, even your oil refineries, they use substantial amount of hydrogen, and that's mainly steam method reforming. And you produce hydrogen, you put in the similar sort of scenarios, store it, and then also finally transport it and use it, utilize in a various energy situation. And apparently, if you have a fossil hydrogen, you must have to capture it, then becomes blue hydrogen. If it is electrolysis green hydrogen, maybe there will be mixture, but ultimately the CO2 footprint of this product should be low. Again, some of the new technologies, gasification, pyrolysis, even biochar, or even fossil coal, carbon black. Because of the methane pyrolysis, you can get carbon black also. That's another product in Australia, one of the company called Hazer process. So that's basically you are producing solid carbon black or carbon product or even graphite. So it's very expensive material, as you know, graphite, because of the battery industry development and demand. So now, so these are the various ways people are thinking about, because you want to reduce the cost of hydrogen. So what if you say make hydrogen from natural gas, you can get some solid product, and that will reduce the cost. But at the end of the day, you can also capture some CO2 in a sense, the carbon is attached to the solid material. So all sorts of configuration are looked at to reduce the cost and reduce the CO2 emission. So if you look at the reforming process, steam reforming, partial oxidation, or thermal reforming, your feedstock could be hydrocarbons, essentially fossil. Operating condition is high temperature mostly. Many of them are commercial, used in various other technologies, various other industries. So you can have that one. So it's not much new really. So but pyrolysis, sometimes that's some of the pilot plants are operating. Coal gasification is well established commercial. There are hundreds of plants operating, particularly in China. You can have biomass. Biomass is also the same thing, not, but again, cost and biomass availability ultimately that somehow you need the feed material. Biomass gasify still is not a lot of plant I have not seen around, and obviously the major one my interest is that green hydrogen, which is electrolysis, alkaline water electrolysis, PEM technology, as you see must. So maybe we will spend some time on PEM technology today, and also SOE, solid oxide electrolyzer, and anionic exchange membrane. So basically two inputs, water and electricity. It's nothing else you need really. Usually some of that, most of these PEM technology is really room temperature kind of condition. So at the end of the day, some of them, alkaline electrolyzer, there are some colleagues say that there are large megawatt scale system, particularly Chinese are heavily promoting alkaline electrolyzer, I can see. PEM commercial, you can get some license through ITM. Hydrogen is a company used to use PEM technology also. Siemens had got now maybe 10 megawatt, 50 megawatt, so it was never heard of, because probably within the below 1 megawatt scale. Now we are talking about 50 megawatt operational. Still, people are trying and learning. I wouldn't say that's fully commercial, but you other one is prototype. For example, solar panels at the same time you produce hydrogen. So you don't need another equipment like that. It's a kind of integrated system. Then other natural hydrogen, probably I will talk about.
PEM hydrogen, how does it work?
PEM hydrogen, how does it work?
Like how is it extracted?
How it is extracted? I will maybe in a couple of few slides later. I'll go more into deeper into the protection membrane technology. So hydrogen from coal, so coal pretreatment, gasify, kind of water gas heat reaction. You get sort of acid gas unit, you get CO2, you get hydrogen, and then kind of lot of recirculation happening nowadays, a lot of optimization so that you can efficient process. So but at the end of the day that's possible. So you need to somehow manage CO2, capture CO2, reuse CO2, so that ultimately hydrogen should be very low or low. That's the objective, to make hydrogen a low CO2 product. And obviously CCS required in some cases that completely free of CO2.
What is water gas shift WGR?
So water gas shift reaction, so that's kind of steam, so it makes CO2 plus hydrogen essentially. So that's yeah, classical reaction.
What is AGR?
Acid gas involving. So that's kind of gas treatment. You have to do some treatment for the gas. So then hydrogen from natural gas, which is currently 50% of hydrogen production is from natural gas, which is steam with an reporting, being the most prevalent production technology with emission intensity of, depending on situation, 7.5 to 12 tons of CO2 per ton of hydrogen produced. So that 12 ton is that generally people look at benchmark, and anything you reduce against that, that's the target. I don't know, 7.5 possible if you run that plant from renewable electricity potential. But natural gas is the major thing. So it's most of the world's, if you go any urea like in Allahabad, if you a fertilizer plant, ammonia plant, any methanol plant you go, that's kind of common technology. So the emission intensity can be significantly reduced about 90% through the integration with CCS, depending on technologies. But you know that CCS is not, also a lot of challenges are there. Due to large reserves of fossil fuels in some countries and well established technologies, I think some countries are favoring a lot of hydrocarbons, then you can think about, but you need to have CCS to reduce what we are calling blue hydrogen. What is CCS? Carbon capture and storage, so that we discussed that that technology some parts of the world they are implementing, and to reduce so that you capture CO2, enrich it, and store it somewhere underground. Now the utilization is slowly coming into, so you can utilize also parts of that. So over long-term DOE, Department of Energy in the US, expects that hydrogen production from natural gas will be augmented with production from renewables, nuclear, coal, with carbon capture and storage, and other low-carbon domestic energy resources. So this is the kind of story of natural gas. This is already well established, nothing to do with shucks. But problem is CO2. So that's just, it will go into a little bit more of that, is still within reporting. So it's natural gas, yeah, and steam you feed together, split feed for reforming, and then generally 2-3 reformers there are primary and secondary reformer, and then natural again water gas shift reaction, acid gas removal unit, and you purify the gas and you get pure hydrogen essentially. So the process for syngas production is starting with pre-reforming and reforming. The autothermal reforming is also a process in which the reforming thermal energy is produced from burning from natural gas. It's kind of same gas is used as a fuel, and once the syngas is produced, the rest of this is stages are similar to the coal to hydrogen process. So majority of the world, as I said, red hydrogen. This is when you stop hydrogen from coal, it's become black hydrogen, and then black coal. It is brown coal or brown hydrogen. So again, I said color I don't like. It's more to be the CO2 intensity. So and this is a kind of new interesting process. Actually, some countries are working on, and actually, in Australian companies they're kind of what they call that raising funds to have bigger plants, and that is natural gas, and you pyrolyze it, and you purify hydrogen, you gas hydrogen, and also the other process depends. Obviously, there is more CO2. But some carbon can be made into a carbon product like either hard carbon or graphite, or I think this company is trying to produce graphite because there is a huge demand for graphite in the world. So methane pyrolysis is a process in which thermal energy is applied to methane gas to break, because methane has got 4 units of or molecules of hydrogen. To break the chemical bond between carbon and hydrogen, which requires a lot of heat, generating hydrogen as gas in a solid carbon product with no CO2 emission. So there is the unique advantage of methane pyrolysis over the conventional steam reforming and coal gasification process. Depending on the characteristics and price of carbon product, its sale may improve the economics of the industrial methane pyrolysis process. So that if you have a pure graphite or some sort of carbon product, you get a lot of the kind of premium product. It can attract a lot of revenue, which can subsequently reduce the hydrogen cost. So it's a kind of multi-product, and one product is hybrid product kind of. So if we talk about biomass again, ultimately biomass is carbon and hydrogen. We call it carbohydrate. So biomass pyrolysis involves rapid heating of biomass, often in cellulosic based. Particles is absent from air at approximately 500 to 700 degrees Celsius. There are various ways, low temperature, high temperature pyrolysis. This results in the production of gas, vapors including water, and solids including mineral metal and charcoal. I think I showed you that charcoal production, similar kind of scenarios. The liquid product fraction collected after the condensation of the vapors is also known as bio-oil or pyrolysis oil. You can remember yesterday I saw 100,000 ton, 20,000 ton is kind of bio-oil. The main components of pyrolysis gas are hydrogen, carbon monoxide. Tar includes all the hydrocarbon compounds with molecular weight above benzene essentially. So chars are problematic in this process because they condense at moderate temperature, cause blocking of the filters and corrosive, and running the plant is difficult. We have run that plant for some time, and we found that even that various matters it's a kind of messy and to run that. But if you can make a clean product, that's probably. So, but again, it is lots of biomass. It is the treatment of biomass. It is another story, and how much biomass you have around, how much you can produce, depends on the country, land, and etc. So in Australia, we have a lot of waste biomass. That's I think many countries has got. But because we have got a strong wood in the forest-based industry, and they produce a lot of waste, potentially that would be utilized. And also, so that's biomass pyrolysis, but biomass can be gasified at high temperature. And then the good thing is that it can take quite a variety of biomass. You can again get syngas, and that can be there are a number of ways. So this syngas is quite flexible chemical precursor, you can say. So biomass gasification process, you can have methanol, ethanol, diesel, even Fischer-Tropsch liquids, which is kind of you can move into diesel fuel or even aviation fuel like planes. Ammonia you can produce, synthetic natural gas, etc. There are some commercialized, I wouldn't say commercialized huge scale, but quite advanced scale in terms of TRL in North America, particularly in Europe also. So despite the development of the concept, it was still commercialized for hydrogen production, because I think the hydrogen amount in the area is limited, and more you purify, and there are a lot of one thing is that if you want to apply hydrogen in a fuel cell, there is a standard now, it has to be very, very pure. So this process may not be able to produce that kind of fuel cell grade hydrogen, but may be possible for blend in the natural gas pipeline. So it depends on where you want to use it.
Sir, if you
Yep.
would compare biomass with your municipal surveys, you
Okay.
have hydrogen versus carbon ratio, and based on which you assess whether this project is feasible or not according to practice.
Yeah, so I'm not sure, but most of the household waste or municipal solid waste, they try to incineration route, but the reason is that it's moist, it's very variable, it's difficult to manage, high ash, hydrogen content is relatively low. But on the other hand, if you have two objectives, whether your objective is the environmental or your objective is the value recovery, economics. So I think economics will struggle probably, but if you put that environmental aspect, because somehow you need to manage the waste. Some cities they are bound to, they are mandatory regulations that you cannot put waste anywhere, you don't really process it. So in that case, probably it's more environmental driver rather than the cost or economics. So I think there are, as I said, that air, steam, oxygen mixture that sort of presents when you use biomass to hydrogen product. But essentially, the technology is very similar, but some people tweak it with several other catalysts or mix. But ultimately, that's the same technology. I would say really two different.
High temperature SMRs are commercially available.
SMRs are more or less not high temperature that much. It's sort of conventional system or commercial available. Yes, that's right. But ultimately, I think you asked the question that electrolyzer. So this is kind of my most, I guess, favorite area, and I think this is the area should be, because ultimately we are doing so much things and it's hard to build the thermodynamic side. So you put lots of energy and you do lots of things, and then finally you get a product, and you what's the cost, what's the so much activities. With this one, I think it's neat in a sense because you get, if you can get enough electricity, that's the key point. If you get enough electricity and then that comes from renewables, then doesn't matter how much you use. So generally in 2020 and 2050 target, and you can say 3 electrolyzer we're talking about here. So alkaline electrolyzer, PEM electrolyzer, solid oxide electrolyzer. So you can see that alkaline electrolyzer, PEM electrolyzer, essentially there is a kind of a proton exchange membrane. So basically hydrogen, so there is a catalyst, there is a water pass through. If you put electricity on, it will break water and oxygen, and hydrogen and oxygen to units, and hydrogen proton will pass through, and then you can basically get the hydrogen as a gas essentially. So that's how it works. Does that answer the question kind of? So that's we'll go into more detail of this each of the individual. I can show you the cell level, stack level, and the system level probably in one of the slides.
Can you explain the difference between all the three technologies?
Okay, so the proton exchange membrane, water is the feed. Okay, water is the feed. Alkaline exchange membrane, that is alkaline means mainly potassium hydroxide is used. So the issue is that here the KOH maybe it disassociate and you get hydrogen, but problem is a little bit corrosion. Managing that difficult, and that kind of, it's a diaphragm, it's not essentially membrane. But what happens is, my feeling is that, or what I know that we can look at some of these specifications, that they are not very responsive for the renewable intermittency, whereas PEM is very good to handle that. If you have power, you get hydrogen, no power, suddenly it shuts down, no issue, and then come back again within a second. So it's very versatile, and that's why if you look at the, and solid oxide electrolyzer, it's the ceramic membrane instead of polymer membrane which cannot do distant temperature. The ceramic membrane can go up to say 700 degree, 600 degree temperature. Okay, so then you can feed steam and you use less electricity to produce more hydrogen. That's the key difference. Okay.
Steam.
Yes.
Steam is the input.
Yes, steam is the input. These two, water is the input. But for steam, you need to have obviously water, heating energy some source. So if you have waste heat, I think this is good.
The membrane is what? Solid?
Solid membrane
This
is the
membrane, solid oxide is the solid ceramic membrane. So
And here? What kind
and
of
here
membrane?
is polymer plastic, basically polymer membrane. That's why that cannot go to high temperature, and that can degrade maybe, whereas ceramic membrane more robust, more strong. So that's the thing. But another thing, if you look at a lot of people are doing this kind of study, what will be the future? Say 2030, 2040, what sort of percentage. So most of these people have different opinions because each industry has their own, they want to promote one. So, but my opinion, overall reading all this, majority will be protection membrane, and that will be probably 50-60%. Alkaline will be maybe 30-40%, and rest will be solid oxide electrolyzer. Because solid oxide electrolyzer is liquid larger place instead of say protonization membrane can be at home, whereas this one I would say more industrial kind of application. That's the one difference. Second one is in terms of technology, these both are much more advanced than SOE. SOE is more kind of still need to sort
In
out.
Australia, what kind of technology is being used?
So proton membrane is we are focusing more mostly.
It has been
So-
installed or it is in the process?
Sorry?
It is in process to install or it has already been installed there? In Australia?
Is that been installed?
It has
So
already been
largest
installed.
electrolyzer we have got probably 2 megawatt.
2 megawatt.
Yeah, but I think there are projects announced like 10 megawatt, up to 10 megawatt, but large projects have been announced for only 50 megawatt, 100 megawatt, and most of them could be built. There are a couple of projects in the outline, and there are some places. I think actually we are running one trial on solid oxide electrolyzer. But if you look at the parameters, so that pressure also another important thing. So alkaline generally sort of low pressure, but you can have high pressure. PEM already within that structure you can have without any compression up to 30, and also with the compression you can get higher pressure. So why you do the higher pressure? You generally 1 to 30, if you go to the compression, you have the staged compression. So early stage of the compression takes a lot of energy. So if you can produce from PEM electrolyzer already 30 bar pressure, you avoid that requirements of early stage of compression. And then you can do that 30 to maybe 80 or 100, 100 to 500 to 700. So because car needs 700, bus needs 350. So that's why a lot of people are favoring. If your application of hydrogen is for transport, I think PEM is a good way to go. That's why. And then SOE is you need to have the gas less than 10 bar and you need to compress it. So again compression energy has to be added. So the target, so that's the target, that's the current scenario. So let's look at the current scenario, let's look at the target. So efficiency, kilowatt hour per kilogram hydrogen. This is alkaline is 50 to 78. PEM is, they are similar, I don't say too much difference to be honest. But SOE, they're saying 45 to 55, actually already people reporting 40. So you can say 40 to 55. So it says not 55, 42 I would say 35 to 40. That's from number. It looks like high. Purity of hydrogen important. All are then 5 nines kind of. You need 5 nines. You can have this sort of if it is 99.9, it's not good for 12 cell. You can have 5 nines purity. So and then lifetime. That's another important. I think you can have any of these technologies, but if that run say 2000 hours and then degrade. So why it degrades? Because these layers are catalyst. So if you particularly high temperature situation, if your catalyst erodes away, then the efficiency goes down. So maybe 2 years down, you don't produce enough hydrogen because it won't drain water. So then that's a problem. And main issue, I would say, any companies have got technology that reliability, because not many projects are running for a long time. I mean, our one we have run for a long time, and we kind of getting the confidence. But saying that I'm confident enough, it's no one can tell that yet. Although there are a lot of testing happening, the longevity of the product is one of the key areas. So some people can sell the product, but you need to ask them how confident you are in terms of the durability.
What does lifetime indicate? Lifetime.
So lifetime means how long it will run. So let's say 2,000 hours
60,000 hours.
or 50,000 hours at stress from continuous run. So it's
Continue
about
without any break.
10 years or I don't know, 10 years is 36,000 hours.
8,000 hours in a year.
80,000 hours. 10 years is 88,000 hours. Even more, from 90,000 right now. So that means looks like if you look at 6 years, 7 years. I think now they have gone up to probably 10. Some people are claiming, but again, at what scale? Is it lab scale? Is it commercial scale? Is it trial scale? So some of the lab is still doing very well, but if you put in a commercial big, then that's a performance required. They are very expensive, and the status is still expensive. That's true, and status, commercial, small scale application, small scale also that one is so. Actually PEM I wouldn't say small scale, I would say PEM and alkaline is similar. This is 2019 and 2020 looks like, but last 5 years a lot of people are doing. So this table has changed a bit, I would say, because that may be, that I would say commercial, this may be small scale, but say 2050, they're talking about, you see that one, that's 100,000 hours, so 100,000 hours. That's the target, so maybe that looks like more than 10 years plus. Like battery life, same with battery. Battery when came about, there were 5 years lifetime, now they're going 10 years, now going even, they're targeting 15 years, things like that. So all of them should be
But what
commercial.
the system efficiency is decreasing?
System efficiency is increasing, is it, or for what's that one? That's
5% decrease, 5% decrease.
So that's that's what called system efficiency, not system efficiency. It's actually that's wrong. It's a kilowatt hour per kilogram.
That is energy cost.
Energy cost. Specific energy footprint. That should
Efficiency
decrease.
is
That
decreasing.
should decrease. And it's a decrease means in
It's better.
It's better, yeah.
So it's a 45 below 45, SOE below 40. I think already a lot of people are kind of reporting below 40. So it's a even to hit target. Some of the things have achieved. PEM, I don't think anyone claims below 52 maybe yet. For some people said 51, 50 maybe, but I think 45 getting there is quite hard. The theoretical energy requirement both is maybe 40, 39. This one would be probably 32. So that's why getting their thermodynamic 100% efficient, it's not easy, right? You need to have some losses and this and that, and so that's the situation.
So what is the approximate cost?
Okay, so then we will go to the one. So the cost is probably roughly you can say PEM and alkaline similar line, $100, sorry, $1,000 per kilowatt at the moment. So people are claiming. A large, again depends on where, how big is economy of the
Kilowatt or megawatt?
per kilowatt. So that's 1 million per megawatt.
1
The same your like solar scenario. But depends, I mean, if you want to install 1 megawatt, that's one cost. If you say 10 megawatt, 100 megawatt, that's obviously possible, right? So we're talking about large scale. Actually, and SOE is a little bit expensive still because of the early stage and etc. So, but BOE target, all of them should be below $100 per kilowatt. Then that will be, it's a bit optimistic, my feeling.
$100 is
Yes,
very cheap. If
10 times the reduction should be 10 times. But remember, all my results I showed you 70% electricity cost, 30% is this kind of cost, and also you've got this is only electrolyzer. It's got balance of plant. With balance of, so roughly 50% is electrolyzer. So even if you make very super efficient, very cheap electrolyzer, still your electricity doesn't
OPEX
come
cost is there.
down. If that doesn't come down, so it has to come down at the same time. The cost has to come down, the efficiency has to come down, the longevity. So you can see now suddenly so many parameters coming into the play and becoming important. So what makes sense? So these are the key parameters anyone want to see by technology or look at technology need to consider.
We are in any perspective, we are still very far to commercially
Well, that's
use it.
maybe because you need to be more efficient. But I think I'm not sure is any Indian company is producing electrolyzer anyone have around? No, not yet, not yet. So because that's why if they see a business, you will see everywhere like mini cars and etc. Right? But I heard that is Reliance thinking of potentially producing electrolyzer. I'm sure there will be battery companies are considering batteries. So it's a new product. So obviously people will be coming slowly. So that's it will go a little bit alkaline. So you both you need deionized water. So this has got, as I said, potassium hydroxide, and so you get water, alkali kind of move around, and then you get hydrogen separation. You can have oxygen as a byproduct, and you can gas cool them and you get hydrogen. With PEM, you get deionized water, again go to the water storage, and that's a PEM stack. You pass water through. There are a lot of what they call that small channels where the water will be passed through, and then you put electricity, it will break into hydrogen and oxygen, and you basically hydrogen goes through the membrane to separate the out. Very simple process in this sense. So you get heat star because there is some water will be taking with it, and you need to add that to the water, and then you get pure. This sort of system is very because responsive to renewable intermittency and also produce very high quality hydrogen and even at pressure. That's the thing. And obviously, ultimately, electricity will be feed to the both places, and they are very similar in terms of electronics. Cost wise very similar, but here because you are handling with lot of alkali, it's a corrosion issue, and here not such thing.
Sir, oxygen purity, sir.
Oxygen purity, that's a question, good question. It's not, it's for industrial application, okay maybe, but for medical oxygen, actually we have one research we need to develop and produce. You need to have another step to get medical oxygen, and maybe you can make some tricks here. That's what we have done, our IP, that it can generate hydrogen, but also medical grade oxygen.
Which is the most cost effective model, sir?
Which one is most cost effective? They are, I think it's hard to say. Alkaline is a little bit cheaper, but as I said, alkaline has other complication. If you appear with that, then that's okay.
Why,
Sorry.
why the hydrogen separation will come back to the water tank again?
Water tank hydrogen separation. So this one.
Next block.
Here.
You are sending the hydrogen back to the water tank again. Why?
So maybe there will be some
Water
will be there, so there will be some liquid gas separation.
residue is there.
That's right. Yeah. So it will be, because sometimes it passes through everything. You need to have a fixed pieces. It's the tricky because you need to have a purity and various stages of purification.
What is the difference between demister and gas cooler?
Demister is more absorbing moisture or vapor or something like that, I guess, that if there is anything left over. Whereas here, maybe they have a little higher temperature compared to here.
Is it like granules form of demister? What is it?
I think it's a standard any absorption system.
Absorbent.
Absorbent system.
Absorbent.
Yeah.
So we have to compress this.
After this is gas lift. This one gas can be 30 bar pressure. This one, this is a pressurizing. This one is a little bit typical. So this one within the system, it is automatically. If you put that in, because this is designed in a way, because of the system, it will create up to 30 bar pressure easily. Without nowadays, they are saying they can produce hydrogen up to 50 bar without additional energy. Just as
So for transportation, what kind of pressure is required to remove hydrogen? What kind of pressure is required to transport?
Transport, yeah. At least I would say 200 bar.
200 bar.
Yeah,
Or
because-
liquefied.
Yeah, not liquefying is even
Liquefied.
lower
In
yeah.
a gaseous form.
Gaseous form. Even say 700 bar pressure in the car, because car has to be 700 bar pressure, 800 bar. Then because when you put injected that one, it will reduce a bit of pressure. Because at the 700 to get it, still it is gas.
In car also 700.
It is 700 bar. It still it is gas, but it is very compressed gas. So if you go a little bit up, maybe it will be liquefied. So near liquefied, but it's not liquid yet. So then solid oxide electrolyzer, so that's operate at high temperature, but we need that heat somehow. It enables favorable kinetics that allow use of relatively cheap electrodes. That's another advantage of that. Both will go into materials area a little bit later. Electricity demand decreases and part of the energy for separation is provided through heat and potential for reversible. And because this can be run, SOE is solid oxide electrolyzer, it can be SOE FC, solid oxide fuel cell. So if you can reverse, it can be giving you power. The same unit kind of, so how you operate it, it can give you a hydrogen, or if you pass hydrogen, it can give you power kind of that.
How is it formulated?
So that's the catalyst changes anode cathode. If you kind of change, because that's the same reaction happens. Solid oxide electrolyzer is producing hydrogen, while the solid oxide fuel cell is producing power. That's the difference. And then this one I'm not too much familiar with, to be honest. That's what I call anion exchange membrane. And some countries, some companies I heard recently, they are very active in this area. Apparently there are some advantages, but I'm not too much familiar with that one. And they said it's a better system and more efficient compared to some other system. So in Australia there is another company called High Setup. That's another kind of they said they have made a big breakthrough that is 95% efficient compared to any of these technologies. They are very government is supporting that one. So, but our understanding is that still kind of fancy scale, a bit lower, small scale works probably, but to make it to larger scale, what will happen yet to be seen.
But I love it, he leverage the capillary.
The capillary, so that's a completely different technology kind of or thinking.
That I was suggesting why don't you pass it to permanent magnets before going to capillary.
Yeah.
Because during my experiments, I observed that when water passes through permanent magnet, it already weakens the hydrogen bonds.
Right.
It accelerates the process. So maybe you may take it forward.
So you know that one that most of these technologies, I think I'll show you some of the equipment that you pass water and it goes through the channels in a very sort of small way. In their case, it's a kind of vertical, and that capillary means water due to gravity falls through, and then there are some capillary effects they try to utilize that, and that way they make it more efficient. That's a claim. But as I said, yet to be seen that you can Google ISATA, they call it. They are in the news for quite a while. But there are friends that came out of Colombo University, the technology, and now they are going to. They've got a good group of people and also raise some funding. Government is backing them up. So because of that efficiency claim, and it is really efficiency in the lab is very high. But whether in the future, what will happen, that we will see.
Maybe in the future we should address the pre-treatment of the water, bubbling
Yeah.
resistance.
So that's another thing is that because many places water is because in hydrogen production water is a key ingredient and that has to be, as you can say, demineralized, so there are advantages because some places there is no drinking water. So if you have additional energy, produce water, send it to the people for drinking, and at the same time additional water you can go to the hydrogen plant, so you get two products. Sometimes many cities, particularly I'm not sure how water is captured here in cities, but in Melbourne, we need 450 gigalitre water every year. So we have a dedicated recycling desalination plant sitting there, not produced even single liter of water, kind of in the last maybe recently, but at least last 5-10 years, it is kind of backup. Because water without water, what will happen in the city? Because we have a dam, we will depend on the water on the dam water, and if some reason there is a drought, then we don't have water, so we run that desalination plant. That was invested initially, it was planned probably a couple of $1 billion, but it took $4 billion. To run this plant, we need to maintain $250 million yearly. So, but we don't use that water. So now can we divert that water to hydrogen? That's number one. Second one, wastewater, because Melbourne City produces significant, with that 450 gigalitre water going through the system and then treated. In our paper, we measure 2 massive treatment plants. So treated, and once treated water, it is drinkable actually, although people don't drink. And you know, Singapore, I heard that people drink, or some countries they drink the recycled water because the quality is even better than the water in the first place we started. But it's a social perception, maybe that's why. But that recycling water can be used for gardening, for other purpose. So what we are thinking, that recycled water, now before discharging to the river or sea, we need to clean it. That clean water is very good for hydrogen. So that could be one. Very minimal treatment is required. So that's what we call wastewater treated essentially. Unused excess water for a place, they have a desalination plant as a buffer, that could be run. And then third one, seawater or rainwater or surface water, depends on what kind of water. But I think here water should not be a big problem, isn't it? Maybe there are plenty of water, but again, where you are located. In Australia, we are targeting desalination, essentially seawater. So then let's move a little bit into natural hydrogen area. So it's called geogenic water hydrogen. So it's like gas field. So some places of the underground, like the gas, a very low amount of hydrogen is there. So we have a big, in my team as well, we sort of looked at that with some other colleagues in geologists. A lot of people are working on this. Is another very hot area. Many companies, oil and gas companies, there because their business in oil and gas, they think, oh, if hydrogen comes in, let's look at that, because they have explored already. So this kind of scenarios we are talking about. So you have got a, that one, you have got oil there, you take it and then you process it, and you run the process plant, maybe renewables or something. So that's at least, that's relatively low CO2 water, hydrogen, and a relatively low cost. So obviously you need to purify and process it. So there are a couple of projects I know in Australia, is 2 companies at least. One company is gold hydrogen, they call it. Natural hydrogen is called gold hydrogen, so that's another color. Yeah, so gold hydrogen got raised some money and quite serious about that company in South Australia. So they are we did effective analysis for that, and one of my team member, Dr. Mohammed, other colleagues, so we can see that one that hydrogen process, and we developed a model, something going in, out, and ultimately get compressed gas. Most of these hydrogen gas field have helium also, so you can have a byproduct. Helium, there is a good demand of helium in the world. So, but which country it has got? So, according to our assessment, production cost is $3, $2.97 kind of per kilogram. So that was the base case scenario. But it depends on the hydrogen concentration. If the concentration high, you can have a very cheap. If it is concentration low, it can be quite expensive. Same with flow rate, because in the gas flow you cannot control. It depends on the flow rate, high flow rate, low flow rate. It is high capex, low capex, because it is a kind of natural material you cannot control. Obviously, discount rate it can vary, tax rate it can vary, and then that's the kind of scenario that sensitivity of levelized cost of hydrogen. So that's natural material. And the good thing, some of the you can say the fast reported techno-economic study on hydrogen in the whole world. Similarly, we did LC of gold, as I said. So if you work with it, kind of, I don't think nobody has looked at that. So now with PEM, so that's our PEM technology. So PEM we work 2 years nearly on hydrogen, plus say 20 years of our work towards the development of technology, and that's PEM electrolyzer. And that PEM electrolyzer is given to a company called Endua, and that Endua at the moment they have got a kind of box, this kind of system. So they say the power bank, they call it Endua power bank. It long duration energy storage products. Self-contained, easily deployable, collectible, on-site hydrogen generation and storage. Infinite, infinite energy storage because you have a 24/7 situation. Scalable, modular, additional energy storage at marginal cost. Yeah, relatively they think cheap, but they have not. You have to, if you want to buy, you have to contract them because they are not. They are selling the product. IP is ours essentially, and we give them any R&D support. So obviously that zero emission technology 100% renewable power when you get. So if you have renewable power, those people are considering seriously. I would recommend that to communicate with this company. So there's a website I can go you later. So our technology, if you we have got actually good chapter on this kind of technologies. So if you look at system level, if you go from eye level, we already talked about. You have got electrolyzer, you have got water, you have got oxygen up, you have got hydrogen, and then you compress it, goes to the storage. So if you go to the stack level, so that's you know that one cell, another cell, it's like a battery. So one cell, one cell probably is those are the material. They call it transport layer, PEL for transport layer. Then this is kind of what we call coated material bipolar plate, and then iridium, that's the anode material, that's the cathode material. Cathode is platinum. Sometimes platinum palladium also can be used, I believe. So that's the cathode, anode, and your membrane, and your porous transport layer, and that's the bipolar plate. That's kind of cell. That's one cell. You have another cell. You have got depending on modular. If you have, so this may be a small unit, smallest unit. If you have 10 megawatts, say you may have maybe hundreds of cells together. Maybe few cells make a stack, 10 cells make a stack, then maybe 10 stacks make a kind of system. And that system has to be so system is not the only thing. If you have balance of the plant, water purification system, water pumping, hydrogen separation, hydrogen storage, compression. So everything together, then maybe a room like this, I would say probably 5 megawatt unit will hold in this kind of room. So that's the kind of maybe even 10 megawatt. I don't know. It doesn't take a lot of space. That's another thing. But it's a 10 megawatt power plant, you can imagine whether it is coal fired or diesel fired, anything, you can have even more footprint. But relatively less footprint, I would say. And very simple operation, nothing running, nothing, no machineries, no reciprocating equipment, etc. Except some pumps, forcing water. Maybe you need to compress, then there is a compressor. Other than that, not much noise, not much equal, not many people required. I've been to some of these plants, which just running unattended kind of. So that's the scenario. And obviously that's the schematic. So that's the cathode, anode, that's the membrane. electricity and water. And to be honest, if you go for solar and wind, there are plenty of solar everywhere, there are plenty of wind everywhere, but harvesting that to an electricity is probably a deal. But still people are doing it. It's not necessarily that it's not doable. It's already commercial. Now, and water treatment technology is super there are hundreds of water treatment plants in the world. So it's a well-established technology. There's nothing to research. So two technologies already well established. Now you need to bring this one in, which is a bit of a challenge. Then you have a system which is decarbonized world. So in a sense, that's not a. That's why I'm hopeful. But to get this system right, maybe it takes a little bit of effort and cooperation and collaboration and international mandate and everything. So I don't know how I'm going with time. So if you look at some of the companies, it's a little bit old hour. We published that Mandar this, but Dr. Mandar this, but one of my colleagues. So that we published this one. I will get that. So that's commercial manufacturer of electrolyzer. So Nail, Norway, still they exist, I think. Cummins, you are familiar with Cummins, right? There are a lot of Cummins in India. So I think in India there is my feeling Cummins, India, this is Cummins, France, they are supplying electrolyzer here, isn't it? Yeah? So if you want to buy electrolyzer, you can go to Cummins, right?
They are not at all affordable. I mean, we will be
It's very expensive.
We go with the corporate in India or something changed. Most of the electrolyzers in India.
Cockerell, they are Chinese, isn't it?
5 times expensive.
So Cummins, so these are the kind of we thought. It's not Endoa, is that still didn't exist. I would include Endoa here, and we have another company for solid oxide electrolyzer. So I'll talk about that also. So and PEM is so that's alkaline. PEM is Endoa should be here. Plug Power, one company, Siemens, OST. I think among them, IT Power, Nail Hydrogen. I think hydrogenics, I don't think they exist. They are taken over by Cummins now. So number of companies producing. Yeah.
Actually, Nell are quite advanced that they are.
Nail. Among them, it's in fact whenever I talk to the people who have bought it and ran it, mixed experiences. So if I say which one is best, it's hard to say.
But they are quite in size, like 20 megawatt there is.
So that one, but I think my feeling is some people complain about Siemens product, but Siemens is, they have so much experience with this kind of industry. I feeling they will come out and pretty well, I think, and obviously among others. And another electrolyzer, AEM electrolyzer, so that's that's a company. So that's we have got actually an actor in this. Solid oxide electrolyzer again, Siemens, hydrogenics. Hydrogenics is part of Cummins now, as I said, maybe. Then there's actually another Sunfire is a kind of most popular company in SOE market. So there are some Japanese companies also I know quite active. Japanese, Koreans also, Koreans. I wish some of the Indian companies will be coming to the play. Reliance Power, maybe as you said, or others may have a product here. Make India programs.
Challenge is not capital materials, which are going to be raw material.
So hopefully that's so let's see how it goes. So that again we sort of it's a more detail of the electrolyzer comparison, what's the electrolyte material, what's the separator, and that's what we spec that. For example, if you go to solid oxide electrolyzer, YZSZ, Ytria stabilized zirconia. So zirconia is very difficult to get around, very expensive product. India has got a lot of mineral sands, and potentially zircon can be possible. And Ytria is a rare earth special product, not rare earth, but critical minerals. And that's why yesterday I mentioned about it. The challenge is some people say cost. I don't think the cost is a challenge. Will be there because a lot of people are working on. Challenge is the amount of material required for this sort of specialty material, particularly. If you look at lanthanum, strontium, I cannot remember, but it's cobalt, and F is I don't know, is that F or maybe LSM also lanthanum, strontium, some metal product, other metals. So these are the special kind of again YZC, that one. So with the solid oxide electrolyzer, the problem is the material is, and same with PEM. If you talk about membrane is not a big deal. This is a polymer, but iridium and ruthenium based catalysts. So iridium and ruthenium market is quite so platinum potentially at the moment platinum is some people say let's replace with platinum with palladium, and actually probably the performance will be same or similar, but sometimes platinum price goes up, sometimes palladium price. So when they started with palladium, looks it's good. Palladium price went up more than platinum. So it's and world's platinum suppliers are in South Africa, Russia. I don't know which country is platinum. I don't know Australia is not platinum. So again, problem is the material, I would say. But here, lot of KOH, but we did not KOH also. But that's another thing. So and also operation. So each has their own pros and cons. So I believe that one of the technology will be, I don't know who will be the winner, really winner. So as we are betting on PEM, but and also the SOE, but maybe other technology will come. Time will tell. Yeah. So again, the bipolar plate, also that each of these material, the frames. Generally, a lot of if you talk about the balance of the plant, it's mainly titanium. Standard steel, even not steel is used overall. So nickel coated stainless steel, things like that. So this sort of technology takes off, it will require a lot of material. So one of our students actually she's a postdoc, Dr. Shalini Dharma from NIT Allahabad. So I gave a project now we are looking at, and also we looked at that. Say whole India, whatever India has got unit capacity, if you want to realize that how much steel, how much aluminum, how much etc. material required, it's enormous. It's a huge amount of material required. So can we divert that currently what we are 100 million ton of steel to renewable energy transition, or you are targeting say 300 million ton by 2035 now, or not 2030. So how much that material you can allocate for your energy transition? That's another question. And so we have already published that. You can Google it, that how much steel and aluminum, this sort of copper, this sort of material required for Indian transition and realizing the wind energy. But also, we recently now looking at how much rare earth is required and where will that come from. That's another question to answer. So again, that sort of table from our chapter, that what is 2020, what is 2025 target. I showed you before DOE target, but alkaline electrolyzer, PEM electrolyzer, AEM, anion exchange membrane, and SOE electrolyzer. And you can see operating temperature, operating pressure, current density, voltage efficiency, electrical kind of not efficiency in a sense, you say specific electrical energy requirements, and then system efficiency. That's probably electrical specific energy. That will be the efficiency then. Load range, that is stack level and that is system level, because you can see that there is when you go from stack to system, you need more electricity entry. Load range and then maximum electrical area, stacks, unit size. And you can see that SOE we are talking about still small, whereas PEM maybe 10 megawatt system we are probably having. So I think that each technology is, a lot of people are working on various technologies, various countries have their different focus, and the Chinese are focusing on alkaline. They have also PEM too, it's not necessarily they are completely doing now. So but I think we are thinking PEM and SOE will be the key technology. And also hydrogen purity, how fast it can respond. As you can see that the PEM is less than 5 seconds, whereas others are higher compared to PEM. Stack capital cost. Somebody asked the capital cost, so that looks like little bit is less than target is. If now they're saying 400, I doubt that is probably most cases, as you said, it's a bit more. But I think that's the highest cost and also lifetime. So it looks like they have ran, although the target is 10 hours, 10 years, but they are less. And so at the moment, maybe 6-7 years, maybe that need to be extended to 10, 12 plus maybe. SOE looks like, yeah, that at the moment less than 20, whereas so that needs to be any question about this, any technologies or confusion or anything like that? Is it very clear? Okay.
Just a question. Like if we start using hydrogen initially, like we have no use right now as of now. So if we start using hydrogen, like in what kind of technology initially at a very low cost that can be utilized in a steel plant?
I think you should look at SOE.
SOE. No, it's all right. Whatever technology may be for extracting hydrogen, but what kind of technology, in what
talking about hydrogen production.
No,
Hydrogen
use of
use
hydrogen.
in the street.
What technology in hydrogen is? That's matrix type, DRI type. That's
Let me moderate.
Okay,
That is a
Hydrogen
big
is-
scale.
Initially, stack injection of hydrogen gas.
No, no.
So what's the question? Can I explain?
Can I
Yeah,
answer?
please. Go ahead.
You got it.
In steel plants, we all have electrolyzers, we all have hydrogen. But coating of zinc, coating of aluminum, coating of magnesium on steel, tin plates, all steel manufacturing units having color coating lines or this kind of coatings, we have hydrogen. We have hydrogen plants installed. In JSW Engineers, we already have 2 hydrogen plants. The Chinese thing, very nice.
So what
Tata Steel has
what do you use it for?
hydrogen.
Hydrogen.
What is the use of hydrogen?
Use of hydrogen. How do you?
What do you do?
Because we wanted to prevent the oxidation of the steel surface. So if you use argon,
Presently नहीं है ना वो तो next plant पे आएगा.
if you are using argon or any other inert gas, it's not going to be agreeable because of the single
You use it for-
hydrogen.
you use it
It's
for-
very, very effective. It does not have any penetrate.
So you allow it for coating of the final product.
It's a bad. I mean, oxygen should not be there when you are coating. For example, you are making auto grade steel.
No,
Automotive
actually,
steel.
वो specialized steel के लिए.
No,
No, in case of structurals and flat products, it's not required.
No,
In a
exactly.
specialized
We don't
product,
have that technology.
Okay, at the moment in the steel plant, do you use hydrogen at all?
No.
No?
No, actually, no. The thing is that no. What he is saying is that it's plant specific. The answer is that plant specific.
Yes.
We don't have the product of color coding.
No, no. The thing is that we are talking about Kanpur steel plant. Kanpur steel plant and ISCO would not have that product. So that's why there is presently no use of hydrogen right now.
What about cooling? Some part of the cooling is that power plant use? Power plants use hydrogen.
No, the blast furnaces in steel sector it's mostly nitrogen, water cooled.
We use
So you
hydrogen at
don't have
our.
on site at the moment no hydrogen at all, huh?
And
Whereas
ICB
power
use
plants
hydrogen
have
for the
so
solar
it's cooling, right? Yeah.
But
But
yes,
this-
we procure from outside cylinders.
That's right. So it's but it's not much use. It's small amount.
Very small.
But it's still yeah, okay. So that's
तो
not.
close loop में रहता हूँ. Close loop for.
And
We
so
are
you
producing.
use
Yeah.
in steel plant or
No,
power
power
plant?
plant.
So that's right.
You are producing hydrogen.
So on site you are producing it instead of the cylinder. You don't take cylinder. You
It's a
produce
small
yourself.
scale. It's a small scale.
What kind of technology you use? Boys, that's a what they call that another diaphragm kind of perovskite technology. So it's a purification of perovskite. So none of these.
Blast furnace there will be
So a lot of them use water, air, and then separate. It's a kind of oxygen plant also use hydrogen, can produce hydrogen. But anyway, there is an oxygen plant in the steel plant, right? What's the use for oxygen for all these BOS and other ones?
No, oxygen is mostly two uses. One is injection in blast furnace and second is steel making.
So if you have a electrolyzer plant, I think your objective is to get more oxygen rather than hydrogen, isn't it, at the moment? Because
And
that's
our oxygen requirement is very high.
Oxygen requirement is quite high.
quite high.
We have 1500 ton per day plant.
So my feeling is that companies like you need to think about pilot plants, small, and try to learn, produce hydrogen,
Yes.
oxygen, and see what is the option.
need
So
to
the
have
first
some
thing is that we need
identify
to
the
use hydrogen. Then only
You
the
need
need
to
for
identify
production
the
is there.
area of usage of hydrogen.
First,
Productive use, productive
What is
use.
going on is, suppose you have a ladle free area.
Land?
Ladle free.
Yes,
Ladle
land.
free.
Hydrogen instead of natural gas or LPG or whatever mixed gas available. People are switching off.
so already we are
Suppose you
using
have
mixed
a
gas.
heating.
So the plant, those were mixed gases, in blast furnace is excess, we are flaring out. So why would someone invest in hydrogen?
So you have excess fuel with the plant.
Yes, we are flaring it out. We are using it to our maximum capacity, then we are flaring out.
So you don't need fuel, you need decarbonization.
Yes.
Yes.
We need
Our
decarbonization.
target is decarbonization.
So objective, so how you can manage that one, that's a different proposition, isn't it?
So let me tell the other applications like reheating furnace with the HSM or any other sinter plant, pellet plant, regulating machines. They are going for oxy hydrogen burner
oxy fuel is like
will not
it includes
use
hydrogen
solar
in that
then.
oxy fuel.
So sounds,
Many applications are coming.
so sounds like in
It's
blast furnace, they are using it.
it's coming, it's okay, but
Maybe
our
after
question is that at the current plant, at the current plant.
plant.
Our question is that at the current plant, what is the hydrogen?
Whatever DRI you can do, but you don't DRI.
We don't have the
At CL there is no DRI right now. But other steel makers
So
are
seems like it's the next 5-10 years when you have new
Yes,
establishments.
new commissioning process.
Immediately no use.
But there are some DRI units already working, independent DRI units.
And
Small
another
scale.
thing, no, another thing you can look at that way, that if you produce some hydrogen, what about the gas, natural gas pipeline? You blend it. Do you think that will reduce CO2, but what at a cost?
So it should be
boiled down by cost.
it should be cost effective than our normal COG and PEM-based LUT.
It looks like there is not, let's change your blast
Technology,
furnace.
we need to change
Yeah, we
technology.
need to change the technology. Last one is as a whole, we need to change that.
Yeah, I got it. I think I got it. That, I don't know, in Bluescope still, they have a blast furnace, but they are using our SOE to get the blast furnace to separate the gas, reducing CO2, but that's again high out, so that's not necessarily their commercial.
Because see, the blast furnace gas does contain hydrogen, so we can separate it.
So anyway, so that PEM technology we evaluated, that looks like this. Electricity is 62, capital
Yes.
cost is 33. Some
Capital
labor,
cost is a one time, electricity, labor and water is a running cost. Capital is a one time cost.
capital is here, but capital, say you get loan. You
Okay,
get- So
it's an interest cost.
interest on capital, essentially that
That is for electrolyzer.
it's a requirement. So it's
It's
everything.
for the plant, for the
So the
plant
plan
as
is
a whole.
100% money you borrow, that's it. Whether you run it or not, you have to pay the tax, isn't it? So that's the money, but sometimes you have your own money. Sorry?
कैपिटल का डिप्रिसिएशन हो रहा है
That's the same, yeah, capital depreciation also. Either it can be said capital
Depreciation or interest both.
or cost for borrowing 80% depreciation. If you don't, kind of borrow, then that cost becomes nil, but still depreciation is there, isn't it? And whatever plan. So that's so roughly looks like 2/3 is the electricity. At least, if you don't ignore capital cost, maybe the result is electricity. So I think that fossil fuel based hydrogen production technology will have a significant role in energy transition period, and that's we see that one, maybe blue hydrogen. So gray to blue to green, that's the conversion we are thinking. There are lots of potential for cost reduction of natural gas pyrolysis as the technology develops by the opportunities for refining carbon as byproducts. So that's a lot of people very seriously thinking about because of the graphite production. And graphite, suddenly there is not much graphite around the world, and they're going to the roof in terms of price. And that's really better because EV market is taken off, and that requires graphite, batteries and graphite, and there are not much. So many companies who are thinking that business, they are sort of investing in that area. And then biomass-based technology also remains priorities where the biomass resources are available, and this technology could benefit from the carbon capture and storage to become a carbon neutral process. Electrolysis technologies such as PEM are developing rapidly, and I can say that because I showed you that some of the activities, and there are lots of potential for new technologies like SOE, which is relatively less mature than PEM, and AEM to take a significant components of the market share. As I said, maybe, but I think 50% market, the current way it is going, it will be PEM, although Chinese are very heavily pushing for money. Natural hydrogen is also another emerging technology that has significant potential and new exploration in various parts of the world are underway. Whether India has got natural hydrogen, we don't know, right? We have got gas, right? Gas field, offshore gas maybe. So if the offshore gas is there, which is H4, potentially there are somewhere H2. So then if that is the case, then people will be extracting H2 rather than H4. I think that's, we have got a very good fuel cell laboratory in Australia, one of the best, I would say, state of the art. And that fuel cell can be used even, this is big truck, I think, what they call BW triple, they call it. So, sometimes yesterday when I was traveling with Hamba, there's big trucks like that. And zero emission hydrogen fuel cell, Panasonic has got the product PCT, there's a company called, yeah, so and BMW has got a new car model like mine, so that's recently, I think, 6 months, 8 months ago, I went to some sort of visit and that saw that car. So I think, any question? So I've got maybe an hour, because I need to spend with you so 1 hour gone, another 4.5 hours, and it's 4 hours at least. So any question about this? We may have a short break before.
So
Yes, yes. Oh,
sir, in the conclusion slide, the second point, can you explain it again?
so which one? The previous slide?
Yeah. Second point, yeah.
So there are lots of potential for cost reduction. Okay, so natural gas, generally lots of people are producing hydrogen from natural gas currently, because that's the main production, which is steam methane reforming. In this case, this natural gas pyrolysis. So there you can get a solid carbon product which can form graphite. So if you get a graphite product, it's not CO2, it's a carbon product, right? If you can sell at higher price, you can make batteries, so that will reduce the cost of hydrogen production, and also CO2 will be low. Does that make sense? Clear?
This thing can happen in power plant where CO2 emission is there. You can also capture this
Power plant gas.
gas.
Power plant gas, the CO2, but there is no hydrogen there.
No.
So you are talking about power plant gas.
So I am talking about the carbon capture.
Carbon capture, you can capture carbon, CO2, then you can enrich and store, but you want to utilize it. Is
It
it
is just making graphite.
graphite? But this is natural gas to graphite. But I'm not sure the carbon CO2 to solid carbon making, that means a lot of energy, and I'm not sure about that process here.
So the one area which is coming up, we are also doing coal tar. After the distillation, we separate carbon. We call the company as excellent carbon in the backyard of our waste. There, eventually, we need to tap at manufacturing.
So, from coal tar, from coal tar,
byproduct में है नहीं destination यूज करते
So,
हैं
yep, any question? You have a comment? All good?
right now the coal tar is being used, is like dumped as a waste.
That's a road construction, easy, that's material.
Only one use, sir.
So yeah, so these materials are very difficult to deal with, I guess. People don't want it here, I guess. Yeah. So unfortunately, some industries are producing it here. So I think let's break for 5 minutes maybe.